Hello and welcome to a video on analyzing polynomial functions, and here we're going to analyze this polynomial function, which is an 8th degree polynomial function. When we analyze, that means we're going to find the domain, the range, we're going to find the end behavior, intercepts, both x and y intercepts, and their multiplicity, and we're going to get a nice sketch of the graph. Also find local max, local min, where the function is increasing and decreasing. So the whole list of things that are there for analyzing are these 7 steps, which I just pretty much named off. But it's pretty much a complete description of what the graph looks like, all of the important details. So let's get started. Now this particular polynomial function happens to be an 8th degree, but it's also factorable. And we hopefully notice that this is a quadratic form because the middle term has a degree of 4 and the first term has a degree of 8. And whenever the first term's degree is twice the second term, and it's a trinomial, that means it's quadratic form. Alright, so in this case, we're going to do a u substitution and let u equal whatever that middle term variable is, x to the 4th, which means that u squared will be that squared, or x to the 8th. Okay, so that allows us to replace our x's with u's. So what we're really looking at here, another way of thinking of what we're looking at, is u squared minus 10u plus 9. And we're looking for 0, so we're going to set this equal to 0. You see how that's the same thing? Given that this substitution u squared is x to the 8th, I just replaced the x to the 8th with u squared. Now I can see this as a quadratic. Now worst case scenario is that this is not factorable, and we'd have to use quadratic formula. So in a sense, we can solve any of these. If we can write it as a quadratic, we can solve it, and we can find some zeros there. But in this case, it is factorable, so we don't need to go to the quadratic formula. We can just factor this as u and a u, and we know that we need a product of 9 and a sum of negative 10, so we're going to go negative 9 times negative 1. Okay, now we're going to go ahead and replace our u's back with the x to the 4th, because u actually equals x to the 4th, and we really don't want to solve this for u. We want to ultimately solve it for x. We want to graph an equation that has x as its variable. So I'm going to rewrite this as x to the 4th minus 9 times x to the 4th minus 1 equals 0. Now these are two factors that neither one of them are fully factored, and they're both differences of two squares. This one is x squared squared minus 3 squared, so this would become x squared plus 3 times x squared minus 3. This one is x squared squared minus 1 squared, so this becomes x squared plus 1 times x squared minus 1, and it's just getting more and more factors, and we're actually not done because this one is still factorable. So let's do one more step of factoring. The rest of these are not. Sum of squares is not factorable. This is a difference, but it's not a difference of squares, so that's not factorable. So we're going to just do one more, breaking this down one more time. So we still have all these other factors. X squared minus 3, x squared plus 1, and this becomes x plus 1 times x minus 1. And now we're looking at a polynomial function, the same one that we started with up here, but now it's fully factored. And this is the form that we are able to most easily find the zeros, because we set each factor equal to 0. So we start out with x squared plus 3 equals 0, and that means x squared equals negative 3, which means that x equals plus or minus the square root of negative 3. But wait a minute, that's not even a real number. That's really saying x is plus or minus I times rad 3. And that's not a real number that we can actually graph. That's why when we're looking at zeros, we're always looking for real zeros. There's no real zeros here, which means that there's no x-intercepts, because real zeros and x-intercepts are the same thing. Okay, so that first factor did not get us any real zeros. Let's look at the next factor. Let's look at x squared minus 3. Well, in this one, we'd say x squared minus 3 equals 0. So therefore, x squared equals positive 3. and x equals plus or minus the square root of positive 3. And those are real numbers. Those are actually going to be x-intercepts. So that's part of it, and these have a multiplicity of 1. There's two x-intercepts there with a multiplicity of 1. Now if we do the same thing here and we continue with x squared plus 1, x squared plus 1 equals 0 is going to have the same problem as x squared plus 3 equals 0. That's not going to give us any real zeros. For the same reason, we would get a plus or minus I times the square root of 1 in this case, but there's no x-intercepts from that one. Okay, we're kind of running out of room here. These two are pretty straightforward. X plus 1 equals 0 means x equals negative 1, and x minus 1 equals 0 means x equals positive 1. So these are two more zeros with a multiplicity of 1. All right, so we've actually found 4 zeros here. And by the way, just as for graphing purposes and looking at the graph, rad 3 is approximately 1.7. So we know when we see the graph of this function, and we're going to look at this in a couple minutes, when we look at the graph of this function, we expect to see an x-intercept at about 1.7, negative 1.7, 1, and negative 1. Okay, next let's look at end behavior. Okay, so end behavior, we don't have to do much searching. If we know where to look, it's right there in front of us. So the end behavior is just y equals that highest degree term, x to the 8th. That's it. Found end behavior. Same thing for the y-intercept. We don't have to look very hard for it because we can do this with mental math. If we know that x equals 0, we're going to get 9 for our, if we said x equals 0, we get 9 for our y-intercept. Okay? Let's look at the graph. So the next thing would be to put this in your graphing calculator, and when you do that, you're going to get a graph that looks something like this. So I'm going to just draw the rectangle so we know that it's on the screen of a graphing calculator, and you look it up in the calculator or on an app. Okay, so now when I put the original function in the calculator and I tweaked the window a little bit, I found a nice screen that gave me a good visual of the function. And so I went from negative 3 to 3 and negative 30 to 10, and this is what I see. Okay, so let's think about what we already know. So we already know there's an x-intercept at negative 1 and 1 and one at negative 1.7 and 1.7. So this is negative rad 3, this is negative 1, this is positive 1, and this is positive rad 3. Now, and we also know that the y-intercept is up here at 9. So this point up here is 9. Now, what would be helpful at this point would be to decide if this is an even function, because it looks like it could be even on the calculator screen, but you can't go by that. You really need to look at the equation to decide if it's even. If it's even, we're going to save a little bit of time. And you can just look at this function and say, well, if it's even, then I know with symmetry this y-intercept has to be right in the middle, so that would have to be a local max. You don't have to search for the local max. Also, once you find one of the local mins, the other one would just have the opposite x. So it's worth a little bit of a glance to see if this is even. Now, this is something you can do in your head. You don't need to write this out, but let me just kind of remind you here that this function, the way we decide whether or not this has symmetry is we just explore. We're just going to explore f of negative x. So we're going to find f of negative x, and the question we want to answer is f of negative x the same thing as f of x? That's what we really want to know. So we're looking at f of x already. Now we can see it clearly. Okay, we're looking at f of x. We just want to know what happens if we find f of negative x, if it's in fact the same thing. So we would go f of negative x equals negative x to the 8th minus 10 times negative x to the 4th plus 9. And when we simplify that, the easiest, you do this in your head once you've practiced it, but just to clarify here, this would be the same thing as negative 1 to the 8th times x to the 8th minus 10 times negative 1 to the 4th times x to the 4th plus 9. That's one way of thinking of it, because this is why the negative 1 just goes away. When you multiply negative 1 by itself an even number of times, it's just 1. So you don't need to put negative anything. So this is really just x to the 8th. Same thing with this negative 1. It's just going to be the same thing as positive 1. So that's still minus 10 x to the 4th. And then plus 9. This, we found this from f of negative x. But that's the same thing as f of x. So therefore, this is even, or in other words, it has y-axis symmetry. So we don't have to do a lot of work here. I'm just showing you how to do it. What you really should do is you should look at this, and after a little bit of practice with even odd, you say, oh yeah, that's definitely even. You just do it in your head, and it takes just a few seconds. All right, so now that we know that this is even, we've already got our local max right here. We can go into the calculator to find a local min. So let's look at the min in the calculator. Okay, so using the min function of the calculator, I found that local min. And because I know there's symmetry, I know that this would have to be positive 1.5, negative 16ths, right? 1.5, and then the same y value. All right, now that we have all that, we have the full graph. We have pretty much everything in our analysis except those last steps: domain, range, increasing intervals, and decreasing intervals. So the domain, because this is a polynomial function, is all real numbers. The range, we can see that the lowest y values are negative 16 in both of these places, and it goes up to infinity. So the range is negative 16 to infinity, including the negative 16. Reading from left to right, initially the function is decreasing until it gets to negative 1.5. So from negative infinity to negative 1.5, the function decreases. From the local min to the local max at 0, of 9, but at 0, we have an increasing, so it's an increasing interval. So it's increasing from negative 1.5 to 0. And then it's decreasing again from 0 to positive 1.5. And then in the very end, it's increasing from 1.5 to infinity. And that's the last stuff that we need in our analyzing the function. So we've got all of this. We've got the graph itself with all the details on it of all the intercepts and maxes and mins, including the scale of the graph. We've got the end behavior, and as a little side note, we got a little review of even and odd functions. Okay, I hope you found this video helpful.